All right, good day. So this is a tutorial on the forming compounds worksheet that I assigned last week, um, and which I promised a tutorial on for those of you who need it. So perhaps if you've already done this assignment, or if you haven't, you can either use it as review, or if you haven't done it yet, as a guide for getting the assignment done completely. So before I go to the actual handout, I want to give a little bit of background on this, just so that you understand, once again, even though I mentioned in class, but I want you to understand the reasoning behind why in forming compounds we crisscross the valences and turn them into subscripts. So what do I mean by this? I'm going to share my screen and give you this background. After I do that, I will get into the actual worksheet itself, so it'll start looking a lot more familiar. But here on your screen is my paint program, and I'm going to first draw oxygen. This might be a repeat for a lot of you who were in class, but oxygen has 8 protons in its nucleus. Happens to have 8 neutrons as well, but that's not important for our purposes on this assignment. Now, when we were determining valences, we remember that initially in the atomic state, oxygen will have the same number of electrons as it does protons. And if we remember the octet rule, we know that 2 of those electrons go in the first orbit around the nucleus. And then the second shell, which should have 8 in it, only has 6 electrons in it. Why? Because 2 plus 6, 2 in the first shell, 6 in the second shell, equal the 8 electrons that we have available to use. But since putting these all in results in a second shell that is not complete, the octet rule is not satisfied, and this atom is not stable. So as we recall, we do for the element what is easiest for it. So our 2 options are: we either get rid of all of the electrons that are in the electron shell that's incomplete, so those 6 electrons would go away, but that requires a lot of work. It would require much less work just to bring in 2 electrons, perhaps from another element that is donating them. Okay, so I'm going to indicate that by an arrow and a number 2. Now, after that is done, this outer shell will now have 8 electrons in it. Okay. Oops. There we go. Oh, too big. Undo. Okay, we'll go back to a pencil here. So now oh, that's definitely a pencil. What was I on before? Okay. I guess it was that one. Okay. So now we have 8 electrons because we brought those 2 electrons in. So since we have a complete outer shell, we can now determine what the valence is. So the protons stay the same. They are still 8. Now the electrons, however, they were also 8 before, but now there are 2 in the first shell and 8 in the second shell. So there are a total of 10. The negatives outnumber the positives, so the valence is -2, because 8 minus 10 is -2. So that is our valence. Okay. Now, when you look, perhaps you have it in front of you, I hope you do, at your forming compounds worksheet, and you look for oxygen, you will see a -2 next to it. It'll look like this. I'm drawing in the upper left corner of your screen, oxygen with a -2 valence or charge. Okay. Or oxidation number, we all know, is another word for valence. So that's why it's got a -2 as a superscript next to it on your worksheet. Now, let's look at hydrogen. Again, this is going to be like beating a dead horse for some of you. Hydrogen has is number 1 on the periodic table. Its atomic number also tells us how many protons it has, right? So it has 1 proton. If it's number 1 on the periodic table, that means 1 proton. It also happens to have 0 neutrons. You probably remember that exception from the determining valence homework. So if it's got 1 proton, that means that initially it's got 1 electron that's orbiting. I drew part of the orbit there and the number 1. Okay. As we know, the octet rule, which, oct means 8, so that's named for the fact that all the electron shells after the first shell have 8 in them to be complete. But the octet rule also just states that the first shell needs to have 2 electrons in order to be complete. So you either need to get rid of that shell, or you need to add electrons to that shell in order to complete it. With hydrogen, the rule just is, for our purposes, that we are going to get rid of the electron that's in the shell. Okay. I'm drawing an arrow here to the left, indicating that hydrogen is going to donate that electron to oxygen. But if you recall, oxygen originally only had 6 electrons in its outermost shell. We added the 2 that brought it up to 8. So those 2 didn't just come from anywhere. They came from an element that was able to donate that needed to donate that electron or share it with another atom in order to achieve stability. So, so we can say that of the 6 electrons in the outermost orbit of oxygen, with the need for 8, we can satisfy one of those needed electrons by reaching out to a hydrogen atom. But that's not going to be enough, because of the 6 electrons in that outermost shell, if we add 1 to it, that only brings us up to 7 electrons. We need 8 electrons in order to satisfy the octet. So what do? Well, there's another hydrogen here. It is identical. It's got 1 proton, 0 neutrons, and it has, therefore, 1 electron to balance out the proton that's in its nucleus. So 1 electron orbiting. Once again, the octet rule is not satisfied. We need to donate that electron. Okay. So we donate that electron. I did skip one little thing here. When hydrogen donates its electron, there is still 1 proton in its nucleus. And after the electron is donated, there are 0 electrons for a valence of +1. So when you look at your compound or forming compounds worksheet, you're going to see hydrogen in there. I don't remember if it's on the first page. I don't have it right in front of me right now. I'm going to toggle to it in a minute. But I know on the second page, on the back of the first page, on that second page there is hydrogen, because that's where I recall we were talking about acids, and pH scale stands for % hydrogen. So there's always going to be hydrogen present in an acid. So we have now oxygen with a -2 superscript indicating its valence of -2. We now have hydrogen. Each of its superscripts indicate a valence of +1. The -2 for the oxygen indicates a need for 2 oxygen atoms. The +1 for hydrogen indicates a surplus of 1 electron for hydrogen. So each hydrogen can contribute to oxygen's need for electrons. And it only takes 2 hydrogens to do that, because oxygen only needs 2 electrons, and hydrogen each has 1 electron to give up. So it just takes 2 hydrogens to satisfy that need. Okay, so you can see by determining valence, you identify on one side, on oxygen sides, the need for electrons, and on the positive valence side, in this case hydrogen, it tells you how many electrons that particular element, hydrogen, can donate to that need. So each hydrogen can donate 1 electron to that need that oxygen has. It's like a fundraiser, right? Oxygen is some sort of nonprofit, let's say, you know, like a local social group or a charity, and they have a fundraising goal. And you know, they reach out to fundraisers, and not every person who donates can donate 100% of that charity's need, but they can donate something. So that's kind of the case here with oxygen and hydrogen. Oxygen's got a need, hydrogen's willing to help, but one hydrogen alone cannot help. It needs a buddy. So it needs another hydrogen that's also got an electron to donate. So if you think about it that way, it makes crisscrossing valences when forming compounds, perhaps it makes that crisscrossing valence trick make a little more sense. Okay, so let's go to the assignment itself. I'm going to toggle on my screen, and I'm going to share the screen with you. Share, we will go over to the worksheet. Okay, so now you should be able to see my worksheet. It's just an electronic version of the exact thing that you have at home. Of course, the first thing you want to do is write your name at the top. I think that goes without saying. However, the first thing that I need to do is turn on my tool that allows me to write on this. And I have to remember how to do that. I'm going to pause the recording for just a moment. Okay, I figured it out. I'll go back to sharing my screen. You'll see the assignment in front of you now. And look at that. First thing, of course, we need to do is write our name. So I'll write my name up top. Okay, and look right there, we have oxygen with its -2 valence. We were just working on that on the previous screen. Now, if you were to combine oxygen with sodium, for example, which is over here, I'm circling it on the left column here, it's going to be a similar situation. Now, sodium's not the same kind of element, certainly, as hydrogen was when oxygen was attempting to combine with it. However, it's got the same valence. How does it have the same valence? Well, because it's got an electron hanging out there in whatever the last shell is on sodium, which I think is the 3rd shell. So, you know, obviously it has more electrons than hydrogen did, but you know, so let's say it fills the first shell with 2, it fills the second shell with 8, and then it's got 1 hanging out there in the final, the 3rd shell, and maybe the 4th shell, but I think it's the 3rd shell. So it's got a similarity to hydrogen because both hydrogen and sodium have 1 electron hanging out there. So the concept is going to be the same. If I were to go back to my drawing program, I could, you know, draw oxygen, figure out its valence, and then I could draw sodium, and I could see that sodium has 1 electron available to share with oxygen. And so it would take a second sodium to give oxygen the second electron that it's looking to have in order to fill its outer shell. Okay, so since I've just determined that it would take 2 sodiums to fulfill oxygen's need, I'm going to put sodium with a 2 subscript, indicating the 2 sodiums needed to fulfill oxygen's need for electrons. So 1 oxygen atom needs 2 electrons. 1 sodium atom can donate 1 of those needed electrons. So a second sodium atom is needed to donate the second electron that oxygen needs. So that's why the crisscross method works. It just makes things a little easier, and that's convenient for us. But sodium now has oxygen's charge as its subscript, and oxygen now has sodium's charge as its subscript. Sodium's charge was a +1, so oxygen's subscript is 1. But remember, in chemistry, we don't write the number 1. The presence of the symbol itself is sufficient. Like I said in class, however, if you want to draw the number 1, it's fine. Cool. No worries at all. Now, let's say that oxygen, which needs 2 electrons, comes into contact with calcium, the second one down here. Your first inclination might be to crisscross the valences and make them into subscripts here as well, right? So maybe the resulting compound would be CaO, calcium and oxygen. I'm sorry, Ca2O2. Calcium's +2 valence became oxygen's 2 subscript, and oxygen's -2 valence became calcium's 2 subscript. But that is actually incorrect. It goes back to the reasoning for the crisscross method. So the crisscross method, like we just did with sodium and oxygen, only works when the valences are different. So, or I should say, when the valences aren't opposite each other, when they are imperfectly opposite each other. So oxygen has a -2 and sodium had a +1. So that's why it took 2 sodiums to fulfill oxygen's need for 2 electrons, because each sodium only had 1 to give up. Now, same scenario, oxygen needs 2 electrons. It always does. That's always going to be its valence, -2. But one calcium atom, just one calcium atom, has the 2 electrons that oxygen is looking for. So in the case where the valences are exact opposites, in this case -2 for oxygen, +2 for calcium, we drop the charges. We just write CaO. Again, because oxygen needs 2 electrons. Each atom of oxygen needs 2 electrons. And calcium, each atom of calcium already has 2 electrons to give up. So for oxygen's need, for one atom of oxygen's need, 1 atom of calcium will come in and fulfill that need. Okay. Let's do, so it would be the same for magnesium, right? Magnesium also has a +2 valence, which means that it's giving up 2 electrons. Oxygen needs 2 electrons. So when you combine magnesium and oxygen, it's MgO. Finally, if we go down to oxygen's relationship with aluminum, it might seem a little difficult. Oh my gosh, now we're talking about an element with a +3 valence, right? So an element with a +3 valence, how do we work with that? Well, we use the crisscross method again. So oxygen needs 2 electrons, but if it's trying to combine with aluminum, aluminum has 3 electrons to give up to it. So oxygen only needs 2. So how is it going to interact with aluminum? Well, now oxygen's going to find a friend. And we could draw it out, and it would take a lot more space than when I was doing my original example on my notepad before with oxygen and hydrogen. So so it would take a lot of space to do it that way. So this is where the crisscross method really comes into play very well. Once again, we're using the crisscross method because the valences don't exactly balance each other out. So for aluminum, aluminum is going to take on oxygen's subscript. So Al2, I'm sorry, it's going to take on oxygen's charge as its subscript. So Al2, and then we're going to give aluminum's charge, aluminum's valence to oxygen as its subscript. So the answer here is Al2O3. Okay. So finally, and this is the last thing I think I'll do on this page, we have SO4 with a -2. Now SO4 is in parentheses. It may seem like this is more complicated, but this is just a radical. It's kind of like, you could think of it as oxygen being a single person and SO4 being a married couple. Sulfur and oxygen married each other and formed a radical. If you want to know what the radical is called, I'm not going to tell you right now. You can go to your element handout where from the first week that says eights are higher than ites. So I know that it's going to be a suffix of 8. And if you're curious, you can look up what the prefix is. Anyway, so for this radical, we treat it as if it's a married couple, and the government, whenever any of you are married or filing your taxes, you can file things jointly. So when you do get into a marriage relationship, you are now treated as one. Even though there are two of you, you become one unit. So when you see these radicals, don't get discouraged or scared of them. Just treat them as one unit. For the purposes of this, if you're doing this in pencil, you can just, pretend it's oxygen again with a -2 valence. It's the same. It won't write now, but whatever. I'm going to be deleting that anyway. Oops, I deleted everything. Oh well, who cares? Well, actually, maybe I can get that back. No, I can't. That's interesting. Yeah, it's not giving me that option. How disappointing. Oh well, doesn't matter. But yeah, like I said, you can think of it as a single element with a -2 valence, as if it was like, for example, oxygen with a -2 valence, if that makes it easier for you. Once you start thinking of these radicals as being single units because of those parentheses, it'll make everything a lot easier for you. So if we were to notice, since the valence is the same, this is actually really easy. If we are comparing SO4, I almost just said the name of the radical to you, so I caught myself there. To sodium, it'll be the same as when oxygen was interacting with sodium. Oxygen had the need for 2 electrons. Sodium each had 1 electron to give it, so it took 2 sodiums to every 1 oxygen. Same thing here. Sodium is going to take on this this ion, or I'm sorry, this radical's charge as its subscript, and then SO4 is going to take on sodium subscript, which was 1. So if you really wanted to, you could draw 1 down here. I'm out of my space, but you could if you wanted to. Notice the 4 didn't change. The 4 is within the parentheses. It's a necessary component of the radical itself. For example, if you look to the right and it says SO3, which also has a -2 valence, notice if I change the subscript there, that it actually turns into a different radical. Much like my example that I've beaten into the ground here of water, H2O. If you change the subscript in water, it would be H2O. Let's say H2O2. You would create hydrogen peroxide, which is much different than water. I'm gonna and then don't forget there down at the bottom here. Whenever you've identified one of these compounds, so Na2SO41, you're like, oh, what is that? I believe it's called sodium sulfate. Okay, I just gave away right there. And indeed, look at this. It tells you that these are all sulfates. Remember also when we were combining, just single elements with oxygen, we said that we would name it, for example, here, when we combine sodium and oxygen, Na2O is the resulting compound. Na2O would be named sodium oxide. How do I know? Because number one, we talked about how to name compounds. We did that in Unit 4. But also, this homework creates a cheat sheet for you. So now you can look at any of these compounds that through repetition you have done in this assignment in order to gain an understanding for how to form compounds. But once you've formed them, you can use this sheet as a cheat sheet so that you can name any compound even easier. So you'll also see down here that if something combines with sulfate, that it is going to also be a salt. So this stuff here that gives you this additional information is going to be useful on the third page here, where we start to actually name the combination of these. So look at this, hydrogen and oxygen on the third part of your assignment here. Quick note though, the first and second pages are your assignment, so the front and the back of the first page. But as you probably recall, once you get to this third page, where it has your name again, I guess, but where you're actually writing out some stuff here, this is where it gets into enrichment points. So you can actually increase the points towards this semester by completing this assignment. Not completing this assignment, however, will not hurt your grade. I should say, not completing this enrichment portion of this assignment won't hurt your grade. You still have to do the first and second page of the the first physical piece of paper that you have, the front and back of that. That's your assignment. You have to do that. If you don't do that, it will affect your grade poorly. But this part of the assignment, this second sheet, is optional and will only serve to increase your grade. It will not hurt you. Okay, so here we have an example at the front of hydrogen and oxygen, which we've been working with all this time. Now, if you were to look, I don't know, actually, I'm going to go back to the previous page. I think this is actually, I don't know if hydrogen is on one of the examples on here. It's not, but that's okay. And this one's kind of tricky too, not because of any reason other than just the fact that the naming is one of the, if you recall, one of the exceptions. So we don't call this hydrogen or dihydrogen oxide, like you would think from the chemical formula for water. We just call it water. Okay, but let's do sodium and oxygen. Sodium, I can use the previous page where I figured it out already. Sodium and oxygen. I already figured out that it would take 2 sodiums for every 1 oxygen. So, so if I'm following the parameters of the assignment, the first thing I'm going to do is I'm going to indicate my sodium, which has a +1 valence. The 1 looks terrible. Plus oxygen with its -2 valence yields, remember that right facing arrow, Na2O, right? I took sodium, or I'm sorry, I took oxygen's charge and made it sodium's subscript, and I did the same thing for oxygen. I took sodium's charge and made it oxygen's subscript. Now, because sodium is combined with oxygen, it is an oxide. What if I don't regularly know that? Like perhaps like, what if I'm a student and not the teacher? Well, I could go back to my first page, which is complete now, to get that answer. So on the first page, when I interacted sodium with oxygen, if I look all the way down that column, it tells me that it's an oxide. So that makes it really easy. Sorry for the dog barking in the background. Actually, I'm going to have to pause this for a second because I have a delivery. All right, sorry to pause it right before the end there, but here we go, back to business. Okay, so Na, sodium, and oxygen create an oxide. And if we go back to the naming compounds portion, the naming compounds portion of our lecture, then we will know that we simply call this sodium oxide. Okay, not all of these are this cut and dry. You will probably need to reference your, sorry about that. You'll probably need to reference your lectures quite a bit. There may be a couple that you just don't know the answer to. And that's why this part of the assignment is the enrichment portion. Okay, so that is all I have for you. If you have any questions whatsoever, please feel free to send me an email or ask me in class, and I'll be happy to clarify anything. Have a good day.